Hello, everybody. Welcome once again to RAGMasters, a show about retrieval-augmented generation. Actually, maybe the only show in the world about retrieval-augmented generation. I'm Neil Katz, a longtime tech entrepreneur. With me, as always, my fantastic co-pilot, Daniel Warfield. You have like 4 titles every time I introduce you: a data scientist, a RAG engineer, an online educator. He once drove a bus around the country that he maintained himself. So Daniel Warfield, welcome again to RAGMasters. How you doing?
Hello. It's good to be here. And we have a guest, I believe, who is a friend of mine. I know, I invited him. I'm super stoked. I think this is going to be a really cool conversation.
Yeah. So since this is your guest, I mean, I usually do the intro here, but why don't you give us the 20 seconds on Dan Lenton, CEO of Unify, and what he does and why you thought it'd be great for the show, and then we'll bring him on.
Yeah, so Dan is a super cool guy. Why don't we bring him on? be cordial about it. Hi, Dan.
Hey, great to be here. Thank you very much for having me.
Yeah, so Dan is the CEO, the founder, right?
Founder and CEO, yeah. And unfortunately, don't really co-founders. Yeah.
Exactly. So the guy, he's the man. He's the man behind Unify AI, which is a LLM routing tool, which allows you to route queries to various LLMs for a variety of applications. It's a super cool technology. We're RAGmasters, so we're going to talk about it from a RAG context, but we'll also talk about it from a general context. So yeah, I guess let's get into it. LLM routing, RAG, all that jazz.
So yeah, maybe just start with, Dan, just tell us a little bit about yourself and about the company, give some of the background, and then we'll jump into LLM routing, what that really means.
Yeah, sounds good. So quick background on my side. I mean, I've had a slight meandering journey personally, let's say. I did engineering degree originally, then PhD in AI, robotics, 3D vision, and then started the company a couple of years ago. We were doing general AI infrastructure, but as of 6 or 7 months ago, we've really doubled down entirely on LLM optimization. And basically what routing means is that the prompt comes in and we send the prompt to the most appropriate model by balancing user preferences for quality, speed, and cost. Basically, this in a nutshell is what the routing does. Now, there are a few different layers to the stack, and I can get into that a bit more, but just for a very quick kind of personal intro and intro to the company, that's, I guess, a summarizing statement, yeah.
And so the core of this, if I get it right, is that it's not always clear which language model is the right one for each job, even literally for each question.
Yeah, exactly. So obviously for a lot of questions, the best performing or the ones that do very well will just be, GPT-4 and Claude Opus and so on. But for many questions that are simple, you don't need such a powerful model. So particularly when you're scaling out your application and you start to care about the speed and you start to care about the margins, the cost margins that is, then a lot of companies are wasting a lot of money and very slow responses on these very large models, which are overkill for a lot of the easy prompts. So this is one of the main things we can do. We can spot the easy ones, send those to cheaper, faster models, and then only reserve the big heavy hitters for the really hard prompts, basically. There is another way that routing can be done that I can maybe get into a bit later, but this is the main way that people are using routing today to maintain the quality of the best models, but make it faster and cheaper, basically. Yeah.
Very interesting. And like, how many, in a typical application that you guys do routing for, how many models do you need in that ensemble? Is it like 2 or like 20?
So in terms of need, 2 is enough. So you can get huge cost improvements with just, GPT-4 and Mixtral 8, 8x7b or something, for example. You can then basically have configurations where maybe 70% of the prompts go to Mixtral 8x7b and 30% go to GPT-4. But when you make more models available, you just have more options, right? So when you take our pre-configured routers, by default, and you can kind of, if you go into the dashboard and you hover over the data points, you can see how many models that these routers are typically using on given data sets. And it's often about 6 or 7 different models. You then just have more options because, of course, if you then have Llama 3 and you have Mixtral small, Mixtral large, and so on, you just end up getting better performance, basically, if you have more options there. But you can get very good routing with only 2. And actually, some customers are limited with regards to the models they can support because they're in GCP, they're using Vertex AI, and they can only use things inside the VPC that they're comfortable with. So it's very useful that our router is very modular because we can then very flexibly mix and match models as customers require in terms of their data privacy and so on.
Yeah, that makes sense. What's the I'll ask one more tech question, then I'll shut up because I really want Daniel to jump in there and get into the weeds. But for the general practitioner, which is the what is the trick of this really is how do you do the routing, right? How do you figure out in near real-time basis where to send a query to?
Yeah. So basically the way we do that is with a neural scoring function. So the way you can think about this is that there's like 3 competing factors, which is the quality, the cost, and the speed. And these are all in competition. You can get things that are very good, but they're typically expensive and slow. You can get things that are not as good, that can be a lot cheaper and faster. And it's about trading off these 3. Now, technically, we split that into 4 because there is the time to first token and the inter-token latency, which are 2 different measures of speed. One is the time you wait for the very first response, and then one is like the streaming speed of the response.
Yep.
And for different applications, they're differently important. Basically, each router has a relative importance to these 4 metrics. And we ahead of time, the prompt comes in, we predict the quality that each model will have on the prompt without having to actually query the LLM. This is with a much smaller LLM that just predicts how good would GPT-4 be at this prompt? How good would Llama be at this prompt? How good would Mistral be at this prompt? So we get all these quality predictions, all of these objective measured cost and speed values as well, crunch it into some big linear combination of like how much to weight each of these 4 factors. And we just send the highest scoring proposal to the user. And then we send it off to the LLM that kind of combines these in the optimal way, basically. There's a lot of details into how the neural scoring function is trained, which is the hard bit, because the rest is just reading from a database. I'm obviously happy to go into that in a bit more detail, but that's the high level of how it works. Yeah.
Very interesting. Dan, you want to jump in here and let's nerd out a little bit.
Yeah, I'm so stoked. So it's really wild because we're probably going to be getting into, I think we've been going for 7 minutes. I think this is going to be the bulk of it. So if I can share my screen real quick, I want to give some backstory, and I kind of want to set the stage for natural language processing as it's kind of evolved, right? And I think this is going to play into what we're going to be talking about. So this all started with a French to English model from the paper called "Attention is All You Need." So these researchers made this model that takes English words and turns it into French words, and they thought, hey, this would be a really clever way to do it. And we're not going to get into the crazy nitty-gritty details of multi-headed self-attention, but basically the nutshell is, if you want to take an English phrase and you want to translate it to a French phrase, you use something called a transformer. Like, this is how they did it. And what the transformer consists of is 2 parts. One is called an encoder and one is called a decoder. So you take your English phrase, like "I am a manager," and then what the encoder does is it turns it into a dense, abstract matrix of numbers that represents the entire meaning, right? That's what the encoder does. And then the decoder, what it does is it takes that abstract, meaning-rich representation and it uses it to generate the translation, "Je suis directeur," which is the translation to "I am a manager," right? So this is an old school way to do it. People don't do this anymore. Basically, after Attention is All You Need came out, they split this in half and they said, let's just make models that are only the decoder, and let's just make models that are only the encoder. The decoder models, where your GPTs, Llamas, Claude, your generative AI models, were this decoder-based model. And there are other models that a lot of people don't know about, but I think we're going to start talking about soon, things like BERT. So it's really cool. I just, like, from a really high level, we started with these 2 components and then we split them up, and now they're almost kind of coming back together again, but in terms of different components, which is wild. So I'd like to talk a little bit. I just wanted to set that stage so that we kind of know what we're discussing. I can get rid of my screen now. So I'd love to talk about these competing factors. And Dan, I believe you referred to as like the loss function that you're optimizing against.
Yeah.
I'd love if you could talk about that a little bit.
Sure. So yeah, the loss function that's being optimized against basically combines these 4 different components. So yeah, there is so the loss function is very simple. It's just kind of A times the intertoken latency plus B times the time to first token plus C times the predicted quality plus D times the cost, basically. And like 3 of those are read from a table. So you have the intertoken latency, the time to first token, and the cost, which are literally just read from a database because they're just objective values that are measured in the case of the time to first token and intertoken latency with these recurring runtime benchmarks that we do every few hours. And the cost is just read from a table. Now, the quality is the really hard one, or is the more interesting one, because that is a model which is, as you are kind of pointing out to, alluding to there, is a BERT architecture. So quite an old one that's kind of came out several years ago. Quite a small model. I think it's kind of, I forgot what size. We have a few different variants, but it's kind of, in the low billions parameters, maybe kind of 1 or 2B is the size we've been using. And basically, what you then end up doing is training that model using GPT-4 as a judge. We actually now use a few different judges, but you use LLM as a judge to predict how good each model, to generate a training data set, which is how good each response from each model was given the answer. So obviously we need to like query all of the different LLMs, get all the different responses to this training data set, and then evaluate all of those responses using LLM as a judge. That then gives us a labeled training set to do supervised training of the BERT model to predict how good would this model be at responding to this question if we were to send this prompt to the model, because we obviously want to predict the quality so we can very quickly make a routing decision without needing to like query all of the models, which costs a fortune, just to know which is the best. That wouldn't be that cost effective, let's say. So that's kind of how it works in a nutshell. There's of course a lot of nuance to getting that system prompt right. And actually sorry, a bit of a tangent, but one of the things our platform really focuses on is for people to train their own router and to be able to define their own judge and define their own system prompt so that you can really customize the evaluation metrics and the trained router yourself. Because we have this foundation router that's a great starting point to play with, but the real benefit comes when you know exactly what good and bad looks like for you. You distill that into your own custom judging function, and then you train your own router with your own labeled data set to really optimize what means good and bad for you in your particular use case, basically. Yeah. And we have all the infrastructure for doing all of that.
Gotcha. If I could share my screen again. So you guys have this really cool UI, which I think you filmed some videos on, your technology, and this seems like it's one that you come back to regularly, right? So,
yeah.
So my understanding is there are a bunch of different data sets and a bunch of different, things to prioritize and things to work on, right? So you take like some data set, right, of maybe questions or maybe question answer pairs or something like that. You take some data set of questions and then you give it to 5, 10, 15 models, whatever. So then you have answers for every question in that data set across 5, 10, or 15 models, right? So every question, you have 15 answers from 15 different models.
Exactly.
And then you get a really big, bad, expensive, fancy, good model to say, was this a good answer?
Exactly.
And then, the good models probably did a good job. But what's interesting is some of the bad models might not have done so bad, right? Sometimes some of the bad models might actually be good at this type of answer for this type of question. So then you build a model, this BERT style model, this encoder style model, the left side of that architecture. You build a model that can predict, given this question and this model, it will perform this well.
Exactly. Yeah. Exactly. And as you say, the reason, and maybe I haven't fully articulated this, I can make this a bit more clear. I think so it's quite rare. It happens sometimes, but it's relatively rare that the cheaper models outperform the more expensive models. But obviously what happens if like the predicted quality on a very easy prompt is very similar between GPT-4 and let's say Llama 3 8B, and they both are predicted to do very, very well, then the loss function that combines the quality, the cost, the speed, etc., is of course going to select the Llama model, because it's like, okay, well, we have this loss function that combines all 4 parameters. The qualities are the same basically, and the other ones are in favor of Llama because it's cheaper and faster. Whereas then, and GPT-4 might even be slightly better. It might be the case that GPT-4 is predicted to be like 95% correct and Llama is predicted to be 94% correct. But because you kind of weight these 4 factors together, the other ones start to outweigh it. And that's where you can see these weighting factors as almost dials, because you can have a router where, let's say, kind of, all 3 of the values for cost and speed are 0, and you only care about quality, and then you're going to route to GPT-4 most of the time. But even then, there's some interest, because that maybe then it routes between Gemini and Anthropic, and there is still like some element to push the performance, but it's not going to ever route to Llama 3, probably. I mean, Llama 3 8B, maybe Llama 3.1 it will. We'll see. We're doing that right now, testing that out. But yeah, that's kind of a way of thinking about it. Yeah.
Gotcha. So you guys have these routers that you've pre-trained, but you also allow people to bring their own questions, and then you pass your models through your 15 models. They predict on your questions, not just some data set. Like if you have questions for your topics, you might have what? How many questions do you need for this type of?
To train a router, you mean? For training a router, we typically see things do well. I mean, you can always get something, but around 1,000 prompts is where things are really working well. Like 250, it can do okay, but I'd say that kind of 1,000 is a good sweet spot. So quite a lot. And you can generate that partly synthetically, but also if you have... One thing I would say is that the routing, when you're doing custom routing, it really makes most sense when you're deploying at some kind of scale. So we very seldom see companies that really do want to deploy routing that don't have at least 1,000, prompts to be training on. So there's normally way more than that, and we can then get very good performance, basically. Yeah.
Yeah. So if I have a semi-successful, burgeoning mom and pop pharmaceutical company, and I have, like hundreds of thousands of questions from my users, right?
Yeah.
I take these hundreds of thousands of questions.
Yeah.
I give them, I'm presuming, correct me if I'm wrong, but I take these hundreds of thousands of questions.
Yeah.
I pass it to your system that then passes those questions to like 15 different LLMs.
Yeah.
Those 15 different LLMs answer the question.
Yeah.
You have probably 1 or 2 really big fancy models that judges the responses.
Yeah.
And then based on this model did well, this model didn't do well, you then train this BERT style encoder to be able to predict how well a model would do in your domain.
That's exactly correct. I couldn't explain it better myself. Although one caveat would be that all of that is customizable. So you don't need to train it on 15 models. It's fully modular. I would screen share, but probably, I mean, the API is in a process of being documented. So maybe verbally explaining it is sufficient for now. So basically when you then upload the first step is to upload the data set, actually. So you kind of just say, here is the data set, here's 100,000 prompts. You can then trigger any model and endpoints to benchmark this on, and you can actually just look at those benchmark results and visualize them in a graph. And you don't even need to train a router. You can just look at, you can just see how they were evaluated. And then you can choose to use those benchmarks as a training data set to then train a router. So it's all kind of very modular how you can do this. And some users might just think, well, we are deploying on-prem. We only care about using GPT inside our Azure instance, and we also have a deal with Anthropic, and these are the only models we care about. So we only want to benchmark these models. So I'm just going to do this first, and then then we want to train a router on top of that, basically. So you can really kind of customize very flexibly how you do this. And the other thing I would say is that it doesn't need to be GPT-4 as a judge. The evaluation can be any model as a judge. You can also customize the system prompt. So we do have this generic prompt that's like, I mean, it's not this, but something like, here is a question, here is a reference answer. How good was this reference answer based on the fact that it should be accurate and clear? Here are the different 5 scores. It can be irrelevant, very bad, okay, good, very good, stuff like this. But actually that entire system prompt can be overwritten by the user. And sometimes people want to add their own in-context examples and say, well, actually, I want to test, I want to test for creativity. So I'm going to say, how creative was this? And here's some examples of really non-creative stuff. And here's examples of really creative stuff. And I don't want to use GPT-4 because I'm paying for this. And I'd rather use Claude on AWS. And I'd like to use my own API keys and use my own free credits for this or whatever. I guess I'm kind of adding more complexity to your very beautiful, simplified explanation of the process. My main point being that all of it is totally configurable. And there's a lot of companies that are quite opinionated on like exactly how the judge works and exactly which models they want to compare against. Because obviously it ends up costing to run all the benchmarking and everything. So it's very customizable, basically.
Yeah, I mean, so I played with Unify because we have a RAG solution. We'll probably get into that in a little bit. But
I do want to make sure we get to the RAG connection.
Yeah.
Here, so
RAG.
Figure out how this is.
Yeah, absolutely. I will say though, it seems like you guys like it's tough to describe, right? Because it's like you have all this fancy stuff, and I see this a lot in AI and software in general. Like you have all this fancy stuff, and you're saying like, oh, we can do this, which is cool. We can do that, which is cool. We can do this, which is cool. But then you go to use it, and then you're like, dude, just the ability to choose that I want to use this model or that model or this endpoint, and just switch it with like a string, is so nice. And I'm like, like we're talking about all this stuff. I haven't had the opportunity to really stress test the router, but it's funny. Like I imagine you can't really sell the fact super well. You could just play around with a different model, but as a data scientist, when you're actually trying to build an application, being able to say we're going to use this one or that one or this one or that one or this endpoint or that endpoint, and then just hot swap on the fly with just.
No, for sure. And there's a decent percentage of our users that are just interested in the single sign-on, actually. So there's a lot of companies that are deploying themselves either as a B2C or often B2B as well, where they just want to have access to all models and providers, and it's a nightmare trying to maintain it. There's things like Light LLM that have their own problems. There's a few kind of options out there, but none of them that really address all the needs. So I agree that's actually interestingly, a lot of customers are fine with that alone and aren't even interested in the benchmark and the routing, at least not yet. So I think a big part of that as well is going to just be getting lots of integrations with the open source LLM space, because aside from building something, there's also awareness building and everything. So there's kind of that ongoing kind of go to market motion and everything. There's also, with regards to the kind of RAG connection and everything, I don't want to give too much of a brain dump, but there is one new side of routing that we're rolling out soon that I think could be quite relevant in that domain. Maybe I'll hold off on just going off on a tangent monologue, but I've definitely got lots of things in that direction that I think
you can bring us, see if you can weave it in, because I just first want to get a general understanding for a RAG engineer. How is LLM routing used in a RAG scenario?
Yeah, good question. So I think to start with, the simplest variant of RAG, which is most people's starting point, is what you might call as naive RAG, where basically all you're doing is taking all of your prompts and what you do is you take all of your information or your context or your PDF documents, whatever it might be, you chunk them and you put them in a vector database so that each segment that you might want to retrieve is effectively expressed as a vector, this kind of big multi-dimensional array. I mean, again, I'm just kind of going very basic. I'm sure many people know this anyway. And then basically the input prompt comes in, and then you do the same with the same encoding approach. You get another vector, and then you do some simple similarity search in the vector space. You find the n closest chunks, and you then basically append that to the prompt that goes to the LLM. And you say, hey, answer this question. By the way, here are 10 pieces of potentially relevant information that you should use if it's useful. Something like this is kind of what naive RAG looks like.
Yeah, so that's RAG in a box. Now, how do you route it?
That's RAG in a box, exactly. So the first thing for that is that sometimes the summarizing model, there's easy and hard tasks for summarization. So basically, it might be like literally all the model needs to do is its summarization step is retrieve some simple keywords from the context and give the answer. There's other cases where it needs to use bits of different information to kind of deduce the answer from the 10 chunks that it received, and that Llama 3 8B would struggle with, but GPT-4 would do fine. So as with any task, RAG summarization has a spectrum of difficulty, and therefore routing makes sense as it does with everything else. But what I would say is that most complex RAG systems are not naive RAG. And actually, let me unpack this a bit more, but I would say that the biggest use case of routing in RAG comes more when you have an agentic hierarchical RAG system, and there are different LLMs doing different subtasks and superset tasks. And there are often smaller, simple tasks like, hey, retrieve the email address from this email thread, or hey, when was the last correspondence? And like the things that a small model can do. And you can then end up actually, instead of having to decide each different level in the agentic RAG system, what model should be used for each subtask, you can just have a router interface and train the whole thing end to end and like learn which subcomponents of the agentic RAG system should be done by a big model or a small model and so on. So I would say the first one is the obvious example. But to be totally honest, not to like shoot routing in the foot, but there's a lot of naive RAG applications where the summarization isn't that hard, and therefore the spectrum of difficulty is maybe not quite as interesting from a routing perspective. But definitely the agentic RAG systems is where you do definitely have, subtasks that are easy, bigger tasks that are hard, and there's a big relevance there. Yeah,
that's interesting. In the agentic scenario, is the routing actually happening on RAG search functions, or this is more like the idea that a RAG search is a piece of a system that has many functions it needs to do, and the agents get to choose, like an agent that does something simple. Might be able to choose a inexpensive model, but when you do the actual at the end, the completion, I guess, when hey, we went and found an email address, identically small model, hey, we went and pulled something from this SQL database or this customer database. You might not even need a model for that. It's just kind of LLM SQL. Now that become injected into the prompt. Now you also have to do the similarity search, the retrievals, and then you've got this bundle of stuff at the end of it. You've got sort of RAG retrievals. You've got the customer support, the customer data. This kind of this big complicated prompt now. Is that the point where you can also use the router, or it's really just on these sub functions that are almost not even RAG? They're just part of building a complex application.
No, exactly. It's much more related to the broader point of the role routing plays in agentic systems in general. So to be honest, the final, particularly when it's a very big complex RAG application, the final prompt is normally best addressed with a big model, because to be honest, as the RAG systems get more complex, that is a very long prompt anyway. Some of the smaller models can't even handle that in the context window. So often, if you have a ton of context being dumped in that's been found from all kinds of different sources, then a big model is most appropriate. So it's more because the best RAG systems end up just being quite complex agentic systems anyway. And like you might still call it RAG, quote unquote RAG, but it's kind of more just like a talk to your data agent, let's say, where maybe it can query the internet. Maybe you have like a special agent that can query this kind of API from Uber transactions, and one that can query transactions from another like database or something like this. And you can then have summarization steps and stuff. So like most of the complex RAG stuff that we see now is more of like a talk to your data agent that includes similarity search as subcomponents, but it's not like, it's not all there is to it, let's say. And the routing is much more about like being able to automatically work out when an easy smaller model is good enough for some of these subcomponents and so on.
I think this is a really important point, because in the first days of RAG, I think people thought of RAG as its own standalone application, but I think increasingly we see RAG really as a piece of an application. It's basically it's augmenting prompts, and a lot of the core of the augmenting prompts is doing similarity search. But that's just a piece of some larger problem you're trying to solve. Unless it's a true Q&A bot, like, hey, I've got 1,000 thing, what's in it? And there's lots of applications. We do this all day long. There's lots of applications in law and health that are exactly that. But to your point, very often RAG's similarity search is just a piece of a larger problem. And I think that's actually the future of RAG. It's not so much standalone RAG systems, but like RAG plugged into an actual product you can use something.
Absolutely. I mean, we had a webinar a few weeks ago where we demonstrated just like some of the shortcomings of naive RAG. It was a webinar we did in partnership with Quadrant, and we just made a really simple agentic RAG system to talk to email, but just like, I mean, like making things fairly that you know they of course would. But if you have your whole mailbox,
Twitter
and you just
demo
have
alert. Twitter
yeah,
calling you out. Twitter demo.
yeah, and you just have your prompt, which is like, hey, when's the last time this person spoke to me? Like, obviously, like that question as a vector isn't going to suddenly find the latest date to today's date and on things like this. So obviously, to actually build a talk to your data kind of experience, you need much more than RAG. Yeah. No, exactly.
Search.
One thing, I won't unpack this too much, but one thing I just wanted to say, particularly seeing as you brought up the long system prompt point, is something that we're currently working on, which is kind of the latest frontier of development. Also not mentioned anyway yet. We're going to be talking about it soon, but you heard it here first. Something we're working on now is actually, so like, one of the biggest problems people have still is getting things actually working. Basically, like there are people that have things deployed and they just now want to optimize their cost and optimize the speed and improve their margins and so on. And that's great. And the routing we've already built is addressing those customer problems already. But a much bigger proportion of people basically they can't fix the hallucinations. They have like 15 different test cases that all need to pass, like these different unit tests or different evaluation styles. They have like maybe a test set of 1,000 prompts, and they have different iterations of their system prompt that they keep tweaking just to try to get everything working. And it's very hard. You keep making your system prompt bigger and bigger and bigger. You add more in-context examples. It fixes maybe 5 of the tests. It causes 2 more to fail. You're not sure why. And people go round and round trying to optimize this. And what is actually very common is that as your system prompt gets longer and longer, as you try to fix all of these edge cases, the very simple prompts start to fail because like maybe like it could answer a simple maths question when you said answer this maths question, but then when you say answer this math question, and by the way, here's 100 examples of like some really hard math questions, and please think about your reasoning and please do this and that, like it can sometimes degrade the performance on the easy stuff. So
I agree with that.
Like TLDR, what we're now working on is a router that not only routes across different models and providers, but actually you can route across different instantiations of the system prompt that basically work well with different subtasks and so on. So you can actually imagine that you have Anthropic Claude, and now you've evaluated every iteration of your system prompt as you're trying to get it working. And an earlier version, 10 versions ago, worked well with these 6 unit tests and these input prompts, and this new one works with these really hard unit tests and these prompts, and you can then basically partition the system prompt space and learn to send it to each of those, and that enables you to improve the quality and maybe this, and then you can do both. Then you can like have different system prompts for each model and different models and all this kind of stuff.
So it's a system prompt router essentially at that point.
Exactly, and that much more objectively enables you to improve quality than we can do at the moment, because actually system prompts are very model specific. So to be totally honest, the mental model that has been employed so far, that we've done so far, kind of assumes that the prompt stays the same and that's unchanged, and we just switch the model and provide it in and out, which actually this is why most of our users at the moment are doing like chatbots and things that are like less on the deep agentic system stuff, because to be honest, that mental model is slightly flawed when you build really complex agentic systems, because the system prompts become very model specific. So anyway, so this is where we think unpacking this to system prompt routing as well is an interesting direction that we're working on.
That is
a cool idea.
Absolutely bonkers. That's so crazy. So like, I want to share my screen. So I wrote an article on React, which is a style of agent. And we just talked about agentic RAG previously. I don't have the slide up, but one of the things that we talked about is tool use, right? So you have an agent, this is a React style agent, and you give it some question. I need to search Apple Remote to find which program it was originally designed to interact with. It was like this hard question where there's like a bunch of dependencies. So it has to search a bunch of different things. So it chooses. So one of the defining things of an agent, most agents, is that they can choose to use a tool. And the way they do it is textually. So they say, I'm going to use the tool search, and then I'm going to search for Apple Remote. And then it observes the response from that tool. And then it decides, I'm going to use search again. So, and then over here, it decides I'm going to use the tool finish. So I'm going to say I'm done, right? So you have these agents that can decide, I want to do search. I want to do pass this to a calculator. I want to do all this stuff, right?
Yeah.
What's crazy about what you're saying is it's like, and we talked about this in the previous one.
Yeah.
The tool here can be RAG, right? So you can like retrieval, you can like retrieve from a database and then do some generation and then observe based off that generation.
Yeah.
But what I'm hearing you say is that like now your tools can be a set of prompts that can change depending on the query. So this tool, in essence, one can think of as a family of tools where when you query, the system prompt changes for the tool itself, meaning that the tool fundamentally changes. So now instead of having tools like hammer, nail, chisel, you have like, I have this multi-tool and I have this multi-tool. And then when you choose this tool, then you can flip through and go, I think the Nick is good. So it's it's turtles like all the way down. Like it's like you have tools within tools within tools within tools. I'm curious, like, how do you think people are gonna like do the right, because it's getting complicated. Like choosing what to do and how to build things. How do you think like just the general design paradigm is going to shift to sort of handle these more complex sort of workflows?
Yeah, I anyone's guess. I'm not sure. To be honest, the way we're starting out, so everything you said there is, like, I think what you end up having is that this kind of system prompt routing, if the different variations of the system prompt, or indeed of the input prompt itself, include different tools being used and so on, like effectively you're routing between different subgraphs in like kind of, your land graph representation or something. So you're basically deciding which kind of graph of different agents and LLM calls to go down, and just learning to do that on the fly based on the data. So that's where things can go. And to be honest, I don't know what the right representation is. There's a big question about whether a static graph, like as the kind of network X approach that LangGraph is doing, whether that makes sense or whether it makes sense for this to all just be much more dynamic. I'm personally of the opinion that things should not be seen as graphs so much, and it should be a much more dynamic thing, a bit more like PyTorch versus TensorFlow analogy to some extent, is one way I kind of think about this. And hard coding the graph ahead of time doesn't make sense to me, really, for various reasons. But at least for us, we're really we want to start this on probably just zero-shot applications and demonstrating it there, because as soon as you get it into an agentic setup where you're choosing nodes within the agent, and that can unroll in lots of complex ways, like just the search space becomes huge. So my mental model of where we start with this is that someone is just doing a zero-shot task, but they still need a pretty heavily engineered system prompt to like address all of the edge cases. And that's pretty common. Like there's a lot of enterprises that have something that maybe is conceptually not that interesting, and the research papers are, light years ahead, but it's got to be production ready. So they need it to pass 20 unit test cases. They need it to never fail. So they have a zero-shot task, and they just need to get the system prompt so it actually is reliable. And like this is probably the area where we would first try to build this out, so that there's not really like tool use even. It's more just a zero-shot kind of thing. But you can just really get the perfect system, or you can get the perfect collection of system prompts to cover as much of the unit tests for as much of your test set as possible, with them all passing, is kind of the idea. And then, then the agent stuff comes later, and who knows like what that looks like, to be honest.
Yeah. What I hear you saying is very similar. It's like when there's a new technology or a new paradigm, it's really easy to go down the rabbit hole of, it could be cooler in this way, it could be cooler in that way. But right now, everything's really cool. We need it to work, guys. So
no, exactly.
Hold on with your fancy mumbo jumbo.
No, exactly.
Tools, multi-tool stuff. Let's like make a few prompts and then test which one is like the least stupid, and then let's do it that way.
Exactly. Ideas can flow orders of magnitude faster than implementations can be done, and also enterprises can actually find the value. So as much as I love to just like live in idea world, I guess it's always one step at a time.
Yeah, you're done with academia for now.
Exactly. It's very different in academia. It's an idea, get a simple demo that kind of shows the idea, then move on to the next toy example. And in industry, it's a bit different.
Well, that's a great place for us to wrap it up with Daniel's thought of let's all aim to do the least stupid thing
It's something I very rarely do, but when you do it once or twice, it works well.
It's not supposed to be aspiring goals, not shooting for the moon, but it may land you somewhere.
Exactly.
Well, thank you, Dan, very much for joining us today. This was really awesome, and
of course,
we learned a ton, and really appreciate it. Thanks for joining us.
It was a pleasure to be here. Thank you very much for having me.
Thanks, guys. See you next time on RAGMasters.